We'll briefly see the topic of rolling friction here. We have seen sliding friction under the context of dry friction in previous videos. This rolling friction is different from sliding friction in that the mechanism of opposing force for movement is different in sliding friction and in rolling friction. In sliding friction, the opposing force is generated because of interference between peaks and valleys in both the mating surfaces. Whereas in the case of rolling friction, the opposing force comes because of resistance to movement coming in because of deformations and restorations occurring as the body is rolling over a hard surface. So let us consider to begin with a body which is rolling on a hard surface to begin with, and then gradually build upon the topic. So to begin with, let us consider we have a hard surface. Hard surface is shown by the red line over here. Let us say on which we have a hard roller rolling in. Let me bring it up so that it's touching. You have a hard roller which is rolling in the direction shown over here, that is looking from this side of the screen. It is rotating in counterclockwise direction under the action of a force P as shown over here. We can at once see that even for very small force P, the roller begins to roll over the surface. But the problem comes in because in real life no surface is truly a hard surface, as we are assuming here and here. No object is really hard. Every object deforms a little bit when it is acted upon by forces or loads. So let us consider a hard roller rolling over a relatively soft surface. Before we see that, let us try to set a little bit of nomenclature clear so that it will be easier for us later to refer to them. We will say that with this direction of rolling, we'll say that this region somewhere over here is ahead. We'll say that ahead of the roller, and somewhere this region somewhere over here we will call behind. So we have two directions, two little regions set up. One is ahead, one is behind. Now let us consider that the surface is soft, the roller is relatively hard. We have a soft surface over here over which a hard roller is rolling. Because this surface is relatively soft, the surface kind of deforms, as you see over here. It follows a kind of a small ditch on the surface in which the roller is sitting in because of its weight. Typically a surface does not deform this much. Just to illustrate the fact, I have shown very large deformation. This kind of deformation generally is not accepted in engineering applications. Just for the sake of illustration, I have shown very large deformation over here. When we try to apply a force P in this situation to cause the rolling to occur in a direction, counterclockwise direction, just as we have seen in the previous case, the roller experiences resistance in this region because it has to kind of climb over the little high place created over here by deforming the material, and in that process it crosses over this region. So you have two regions here, one region in which your deformation is occurring and the other region where your restoration is occurring. Okay, as the roller is rolling, this deformation region will also be moving ahead. That is, when the roller is rolling, this roller continues to deform the region ahead of it. While it is doing, the region behind, which was earlier deformed, kind of restores its original position. So we say that this deformation region as well as the restoration region, both of them move along with the roller when it rolls on the surface. We'll try to see a little bit more about it by considering what kind of normal reaction is exerted by the surface on the roller. For doing that, we'll draw the free body diagram of the roller and try to consider all the forces that are coming on it. By a slight abuse of notation, I'll use this picture itself that is shown over here as a free body diagram to illustrate what is the normal distribution. The picture here shows that several normal forces occur. In fact, there is a distribution of normal forces across this entire region that we have shown over here, and we call it the distribution of normal forces. In general, the normal force is a little bit more at this region which is ahead, and a little bit less in the region which is behind as the roller is rolling. That is because the region ahead of the roller will be deformed, that takes in energy, whereas this restoration releases a little bit of energy. To simplify the situation a little bit more, we will consider two regions, maybe one region approximately to the left of this line and one region to the right of this line. We find kind of resultant of all these forces in the ahead region and resultant of all the forces in the behind region, and try to see what is the resultant of these two resultants. The two resultant forces are shown over here. One is ND to indicate that it is in the deformation region, and NR to indicate that it is in the restoration region. Because this ND and NR both are coplanar forces, we can very easily find their resultant by using the triangle law. So we draw the vector ND to begin with, something like this, and from the head of this ND we draw an R as shown over here. Again, as we saw, we don't know exactly what is the distribution of the forces, and so we don't know what is this ND and what is this NR. But we know that once we know ND and NR, we can find the resultant by drawing the force triangle. So the resultant of these two forces, which are shown as two sides, one ND, one NR, and the closing side gives the total resultant N. Now let us show this total resultant N on the free body diagram and see what we get. To redraw the free body diagram by showing this net resultant N as given in the force triangle, we try to consider this roller in itself, which is a hard roller, and try to show all the forces on it. We have one force, that is its weight W, acting vertically down, and another force is the external force. Let me try to redraw the force correctly. Vertically down, this is W, and we have another force which is the external force P acting on it. This P also we will show this way, and the third force is the net resultant N. If we assume that this roller is rolling with constant velocity. If we assume that the roller is rotating with constant velocity, we can say that it is in equilibrium, because we defined equilibrium to be either when the body is not moving at all or when it is moving with constant velocity. If the roller is rotating at constant angular velocity, thus giving constant linear velocity to its center, we say that it is in equilibrium. When it is in equilibrium, acted upon by three forces, out of which we know two forces W and R meeting at a point, this W and P meeting at a point, we can conclude from three forces in a plane theorem that this N must also pass through that point of intersection. Let us designate this point as A and take moments about point A to find out the equation of equilibrium. Knowing that N passes through O, note that this point of intersection A is not on the line of action of force W. Let us indicate that distance by this quantity lowercase letter a. With this distance A marked and the angle theta as shown over here, we can see that this distance from the line of action of P to this point, the vertical distance between them is r cos theta, where theta is shown over here. We now write the equation of equilibrium as sum of all moments about point A to be equal to 0, which gives us W multiplied by A is equal to P multiplied by R cos theta. Usually the deformation we have shown in the picture is very large as suitable for explanation, but the deformation is very small. Consequently, this angle theta is also small. Theta tends to 0. So this cos theta is approximately equal to 1. In which case we write P is equal to W multiplied by A over R. This we say is the equation for force required to start moving of this roller at constant velocity. This quantity A is called coefficient of rolling resistance. Since A is having the dimension of distance units, the coefficient of rolling resistance has a units of meters when we measure distances in SI units, or it has units of mm. Typically A is very small. That is the reason why we say rolling friction is very small. But what we actually mean is rolling resistance is very small. In some parts of the literature, this equation is written as P is mu r times W, where mu r is called coefficient of rolling friction. So when used in this context and call mu r, which is equal to A divided by R, as coefficient of rolling friction, this quantity is dimensionless. It is worth remembering here, coefficient of rolling resistance has a units of length, whereas coefficient of rolling friction, which this term is sometimes used in the context of SAE, Society of Automotive Engineers, or in the context of railways. This coefficient of rolling friction